Okay, Assalamualaikum warahmatullahi and selamat sejahtera. So today we will go to the part 2 of program design. Okay, so the learning objectives for today are understanding the characteristics of a quality software design. So you want to create a software, you want to design a software. So what are the quality characteristics your design should have? So explain good design principles and analyze the benefits of applying good design principles. Okay, so design quality. So what do you mean by a quality design? So design quality is an elusive concept. What does elusive concept means? Means that there's no really one answer for a design. Okay, like if you give me different designs for your assignment or for your final exam, for me it's fine as long as it's logical, right? However, in real life, the quality actually depends on the specific organizational priorities. And even though a good design is flexible, there are a few principles you have to follow to make sure your design is good. So a general guideline is a good design is the most efficient, the cheapest, most maintainable and most reliable. So when you say efficient, if it's supposed to respond in 5 seconds, it shouldn't respond in 10 seconds. Right? So the cheapest, most maintainable, if you can create it with the minimal lines of code, if it can be created with 50 lines of code, don't write 100 lines of code. Right? It's also most reliable. So the attributes, criteria that we discuss here will be related more towards the maintainability of the design. So design quality, the principles that we're going to talk about today shall apply not only to object-oriented design but also to function-oriented. So what's the difference between object-oriented and function-oriented? So your function-oriented is like your DFDs, your data flow diagrams, right? It's called a structured or function-oriented. So object-oriented design is grouping your data more towards data abstraction, right? So we'll talk about it in detail. So there are 1, 2, 3, 4, 5, 6, 7 design principles that you should follow when you start your design. Abstraction, modularity. So modularity is coupling and cohesion. So what's coupling, what's cohesion? We'll talk about it. Information hiding, limiting your complexity, right? And it's good to design based on a structure, top-down approach. And your design must be understandable and adaptable. So let's look at it. Abstraction again. So what's abstraction actually? So basically abstraction is modeling it or drawing your design in a way that it represents a complex reality in a very simple way. Okay, like in this case, a duck is complex, but it's being modeled or abstracted by just one single block. Okay, it's a joke, right? Okay, so there are many levels of abstraction. We have a higher level and we have a lower level. So the higher level would be an overall system, like the abstraction of a clinical information system would be, clinical system. So when we talk about the subsystems, you talk about the modules. What are the modules you have in the what are the subsystems you have in the clinical system, and then you go down into the modules in the subsystem, right? So let me talk about functions, right, in the subsystem, functions in the modules, right? Okay, so what are the type of abstractions that are available? So there's two types. Basically, one is a procedural and one is a data abstraction. So this procedural abstraction is a name where actually represent a sequence of activities, like open a door. So the name open represents a level, a sequence of activities. That is, you walk to the door, you hold the knob, you turn the knob, pusing tombol, and you pull the knob. So one word open the door actually represents 4 or 5 lines. Right? So in your model, when you model it, you have to choose a good word which represents, is a good way of representing the sequence of activities, right? Then we have data abstraction. Right. So data abstraction is a name collection of data that describes a data object. So this is more like your Java, which is also object oriented. Like when you name student, you would actually kumpulkan or collect all the student attributes, functions, in one class. So you're abstracting all the, you're grouping all the related data in one class, student. So that's a student abstraction. Okay. So for data abstraction, there are many levels. We have a view level, logical level, physical level. So the view level is just saying, it's a student class. When your logical level, you're putting more details in it, like what are the attributes, what are the functions in it. And your physical level is basically your coding, right? So that's how you do abstraction from your code. You do to an ERD or a class diagram. Then so the view level is good for customers, your clients. Logical level good for designers, for them to communicate between the requirements and the implementation team. And the physical level is usually for the implementation team. So this is basically a summary of the level of abstractions. So the lowest level is basically your machine code, 010101, right? So then the highest level is your modeling languages like UML, right? TFDs. So that's done. We're done with abstraction. So now let's go to modularity. So that was the first point, abstraction. Second is modularity. So what's modularity? So most of us as programmers, so the number one excuse, not excuse, I say. So when you program, when your code is compiling, you're like, okay, it compiles, that's fine. You think that it's a good achievement, that it compiles, which is partially true. Compiling is one, but is it a good design? Is your code a good design? It may work, right? But you can write it in 50 lines, but you're writing it in 100 lines. So basically modularity talks about cohesion and coupling. Are you very difficult words? What's cohesion? What's coupling? Right? So basically cohesion is you imagine houses, like we have two houses, which is like two modules. So one house, there are many family members in the house. So cohesion is how often these family members interact with each other. And coupling is how, one house interact with the person in the other house. So cohesion is your modules in your subsystem. So how do they interact with each other, right? So in coupling is how is the interaction between different submodules, right? Okay. So yes, cohesion is how well a component fits together. Okay, so I want to show you yes, this is the one I wanted to show you. So what's coupling? So basically coupling is how much interaction there is between different modules. So a tightly coupled system is modules interact a lot with each other. A loosely coupled system is modules they don't interact much with each other. So what do we aim for actually? So we for a good modularization is we have a high cohesion and a low coupling. So as you can see, this is a high cohesion here, right? So you can see nodes 1, 3, 4, 5, or maybe you can call it modules or functions. 1, 3, 4, 5, they interact a lot with each other. They call each other often, right? But module A and C don't interact much. Only function number 5 can call function number 8, right? So means that this is a high cohesion because it has been grouped very well, right? The functions that interact with a lot of each other are grouped together in a module. So it's a good modularization. So bad modularization is when there's a low cohesion and high coupling. Right? So what's a low cohesion and high coupling? So high coupling means there's so much interaction here, you see. See, function 5 can interact with function number 8. Function number 10 can interact with function number 6, This is a high coupling. So we aim for high cohesion, low coupling. Okay, that is the good design principle. Good modularization. Okay, so we want to avoid low cohesion and we want to avoid bad modularization. Okay, now for information hiding. So basically information hiding is hiding your secret information, hiding your algorithms, hiding your data structures, So why do we want to hide it? Number one, for security purpose, like we don't want hackers to know your algorithm so they can, hack your system if they know the flaws. Okay. And also for also IP purposes, like Google hides their ranking algorithm. People actually pay to post an ad, keluar iklan dalam Google, orang kena bayar, right? Semua orang nak kerja, siapa dapat number one, whose ad is top ranking, right? So if I have an online shop selling baby clothes, let's say, so I want my shop to rank top when a user search for baby clothes, right? So, but I have to compete with other shops, right? So I don't know what Google algorithm is, what I can do to actually make my website to be on top, right? So it's a secret because it involves money, commercial. So yeah. So that's one reason. Um, Commercial reason, business reasons, security reasons, right? Okay, so that's information hiding. Then complexity. Okay, so basically, less code is cleaner and maintainable. Keep it small, right? So the less complex your codes are, your design are, then the better. So it's a design principle. Keep it small, keep it clean. Okay, right. So always a top-down design. Okay, so go to the next principle. So what does this top-down design means? Means that when you start designing, you should start designing from the top. So what's the top? What's the bottom? So you should start designing from an overall system first. You know, like your DFDs, data flow diagrams, we have a context diagram, then we have a level 0 and a level 1. So the top-down design is you start with level 0 first, then level 1, and level context, then level 0, level 1. Right? So that is a recommended practice to start designing top-down. However, in reality, large systems are never designed truly top-down. Some modules or branches are designed right from the other. Right? So, best design is a top-down approach. Right? So you design it from the system level to the subsystem level, right? Top-down approach. Sorry, my writing really terrible, right? So, however, in reality, in large systems, it is not necessarily that way. Okay. So the next point of a good design is understandability. So if another programmer another designer, programmer reads your documents, your codings, your designs, your requirements, can they understand it? Someone who has no background of your system, can they understand your design? Are your names well named? Like for example, your name variable is called ABC. Nobody knows what ABC is. Variable A, variable B, variable C. You can name it variable first name, variable last name. So the naming convention is important, right? So is the cohesion strong, right? Do the modules, the functions in the same modules interact a lot with each other? Alright. Are they grouped well? Is the documentation easily understandable? Okay. Right. And are complex algorithm used, or are your code simple and clean? Okay. So we want to avoid high complexity. So it is your design is more understandable. Right. Finally, the last criteria is adaptability. Okay. So what's adaptability? Basically, your design is adaptable if the components are loosely coupled, high cohesion, good modularization, right? Well documented, And very important thing is it has a design visibility, means that it's traceable, so you can trace your code back to your design document, back to your requirements, right? So it's adaptable, right? You can trace it and you can find the links. So if you want to change anything, you can relate it to which part of the design, which part of the requirements, right? If you're changing a code, let's say, so you can trace it back to which design and requirements which maybe need to be changed as well, right? For example, right, so your requirement is avoidance of falling metal blanks, right? So this is your description, right? So then you say a fit, and one of your requirement is a fit belt conveys a blank to table if okay. So this is an engineering requirement. I myself not very clear what does it mean. What's a fit belt? I have no idea. But what I'm trying to say is that there's a traceability. So due to this requirement, they actually have a fit belt class here and a table class here. So you can trace the requirements to the design, to the class diagram design, right? Right. So, and it says, blank here, it has a add blank here, so it's traceable, your functions traceable to your requirements, so your design is adaptable, right? So this is also talking about design traceability, right? So your design here is traceable to the lower level of design. Okay, so basically, finally, design is a creative process, right? It's creative as long as you keep to the design principles that we mentioned. Okay, so I hope you have really understood the characteristics of a quality software design. You can be able to explain what are the good design principles and also understand and analyze the benefits of applying good design principles. Okay, thank you very much. Bye.